water. If we take residential and non-residential buildings together in most developed countries, we're talking about 40% of the primary energy use, and they produce a commensurate share of pollution as well. So buildings are important if we think that these things are important. We aren't doing terribly well yet in terms of having the balance between quality of life and sustainable life that we would like to have. This is an interesting chart put together by the UN it's a Human Development Index of the United Nations, and it shows how different countries relate in terms of their quality of life on one axis and their ecological footprint on the other. And we would like to have our points here in this little green rectangle at the top, where we have a sustainable environmental footprint and a quality of life index that's high enough. And you see that the countries that have a sustainable footprint, for the most part, have low quality of life, and those that have high quality of life by this index have a large footprint. And apparently only Cuba is doing things right, which shows that there are benefits to being blockaded by the US for 50 or 60 years. I'm not necessarily recommending that as a political strategy, but you know, with our current president, anything can happen. So let's move on to thermal storage specifically, and a very brief review for those of you who are not thinking about this frequently. It's simply the production of cooling capacity at one time so that we can use it at another, and the modifications that we make to our mechanical systems to do this essentially separate the shape of the cooling load profile from the shape of the plant operating profile. And so that allows us, if we have enough storage in our system and know how to use it, to optimize both the size and the efficiency of the plant. The things that it does are primarily reduce peak loads, so it makes equipment smaller, and it also increases load factor on that equipment, which is also generally associated with cost effectiveness and efficiency. So that's a good thing. And in case the load factor is not a familiar concept, that is simply the ratio of an average load to a peak load. Could be a thermal load, could be an electric load. When load factors are low, what that means is you have a lot of generation capacity that's not utilized very much. You may have to have a very large electric generating plant or chilled water plant simply to meet a peak load that occurs a few hours in a year, and maybe not even every year. If we can do something to increase a load factor, then the plant size and cost becomes smaller, and it tends to operate more efficiently, as I've said. Thermal storage can increase load factors for the cooling plant itself. So locally, the thermal load factor can increase the load factor for the electric, for the site electricity, because typically there's a lot of electric power going into cooling systems, and that aggregates to a beneficial effect on the load factor of the grid. So the building is connected all the way back to the point where power is generated. Here are some examples of typical profiles for something like a district cooling system for an urban center or for a campus. They tend to have large flat loads, and the load factors are fairly high. The horizontal orange line there is the average load, and we take the ratio of that to the peak of the actual load profile. The blue line to get the load factor that's shown. So for this one, we have an 83% load factor. Something that's more typical of a school or office, where there's high occupancy for a few hours during the middle of the day and no occupancy at night, is shown on the right, and that's a fairly typical load factor as well, something below 50%, maybe as low as 30%. So there's opportunity in both of them to increase the load factor. Clearly we can do more with the school or office type of load, but actually the large district cooling type of loads turn out to be very good candidates for thermal storage for other reasons, mainly associated with the economics of large systems. The electric grid has load factors that are not terribly different from the thermal load factors that we see for different types of cooling loads, and that's because a lot of the electricity during the summer, which is typically the peak period, comes from cooling. A summer day load factor for Pacific Gas and Electric for one of its types of rates shown there in the figure is about 63%, while in the winter it might be 90%, but the annual load factor, the capacity you would have to meet the average annual load compared to the peak load for the year is only 29%. So that means that the people who buy electricity from that utility have to pay for 3 kilowatts of generating capacity for every average kilowatt of capacity that's actually needed to meet the load. So to the extent that you can move that peak in the direction of the average, rate should go down. So when we're doing thermal storage, we have to move around cooling capacity. It's illustrated here. We have a production unit, the plant that can produce cooling capacity, and it delivers it to the end users, wherever they might be, an air conditioning application for an office or a data center or some other process. This is the non-storage scenario in which whatever the load is determines what the plant produces. When we add storage to the system, by taking stored cooling capacity out of it, we can now use an arbitrary combination of direct and discharge capacity to meet that load. But of course, to be able to do that, we have to have a point in our cycle where we put cooling into the bank, if you will, which complicates the system's design and operation a little bit, but actually not terribly much. Again, we see that just in the structure of the system. Here's a non-storage cooling system, and we can see the direct connection between the plant on the left and the loads on the right. In a system with thermal storage, such as the small ice storage system shown here, we have the ability, there it is, there's a pointer, to meet cooling load directly from the chiller with no storage. Chiller could be off and we could be providing capacity entirely from storage, or we could be blending water that's partially cooled by the chiller with water that's diverted through the storage to meet the load. So there are many different configurations here that to some people's thinking add complexity, to other people's thinking they add flexibility and the ability to do more and better things with the system. The benefits of storage that are normally noted start with electric cost savings. And this was almost entirely the driver for thermal storage if you went back several decades. Users of electricity are charged for the peak capacity that they require, as well as for the total amount of energy that they use. So peak demand reductions lead to savings in demand charges, and shifting of energy use from one time to another to accommodate the operating characteristics of the generating grid will be compensated. You'll be rewarded for that with a differential cost, cheaper at night than during the middle of the day. The big question, and this is where we get into the issue of sustainability from the point of view of energy efficiency for thermal storage, is do we save energy either on the site or in source and transmission? And we'll explore that possibility a little bit here as we go forward. The other potential savings from thermal storage are capital cost savings, because when we take advantage of load shifting to make the peak load smaller, then many things are smaller and less expensive. So chillers and their ancillary equipment, cooling towers, pumps, piping gets smaller, maybe the electric service. And if we have a cold source, if we're using ice storage, for example, then it's possible to make lower temperature water and air distribute, which may reduce the distribution energy as well as the cost of ductwork and piping. On the other hand, that trades off with the cost of the thermal storage component, so I can't tell you that you can always save money with a thermal storage system compared to a non-storage system. But when you are considering something as large as a district cooling system that will probably have a stratified thermal storage tank associated with it, it's quite possible to have a lower capital cost for those systems than for one that was a direct refrigeration only system. And as a retrofit, this is a good way to increase capacity as well. So that's some of the benefits on the economic side. As I was mentioning briefly before, the recent history of thermal storage has been that this whole model of thermal storage as a way of saving money by playing around with your electric rate has fallen apart, and so that was in the US very directly related to deregulation. But I think everyone was at one time looking at thermal storage as a way of saving energy cost and not so much as a way of saving energy. So this is what we need to focus on if this is going to be a technology that we continue to use in the future. So how can thermal storage support sustainability? Well, we can try to get those site energy savings that I said may or may not be available, and determine whether it's really possible to have source energy savings as well. When we save energy, we reduce emissions, so that's sustainable as well in terms of improving air quality. And also, I think there's an opportunity to use storage as a way of enhancing the use of renewable energy sources that are not continuous. So particularly we're thinking of photovoltaic and wind power, and I'll comment on that briefly here as we go forward too. So let's look at the issue of site energy, and we'll look at this with a very simple example of only one day. You have to imagine that this sort of effect that I'm going to show here could be carried over from day to day and would actually result in an aggregate savings. So one of the main things that happens with thermal storage when you move the production time from on peak, when it would have been needed to meet the peak load, to off peak, is there should be some improvement in condensing temperature. And for air-cooled systems in particular, the day to night condensing temperature difference can be quite significant. So we might be talking about something that's approaching 10 degrees C difference in daytime to nighttime air-cooled condensing temperature. There's a difference for wet bulb from day to night, but it's not quite as large. So there you have to take your efficiency benefits from having a water-cooled system to begin with. So that's always going to be helpful. Ice storage, I will freely admit that I'm not a big fan of ice storage, because when I was a consultant, I mainly worked on large systems, and I couldn't quite justify dealing with the energy penalty that comes with ice storage from having to use such a low evaporating temperature to make it. So if your goal is to save energy with thermal storage, the best way to start is probably not to dig yourself a big energy hole that you have to get out of in other ways. But actually, you can still have an ice storage system that in some cases will use less energy than a conventional system if it's air-cooled and if you're using the low temperature source advantageously. The biggest issue, I think, with ice storage is, do we actually have an application requirement that needs a temperature that's a few degrees above freezing? If you do, then it's a great idea. But if what you're trying to do is high temperature cooling, use the warmest temperature possible, then you're clearly wasting energy by making that with a very low temperature source. Just like if we're trying to heat a building with low temperature hot water, having combustion sources that are 1,000 degrees is not a good way to do that from an energy and exergy point of view. Chilled water, because it doesn't necessarily alter the operating temperatures of the system, tends to be very compatible with a low energy approach because there's not really a charging penalty. So we're going to look at an air-cooled example here, and I'm going to assume that we're dealing with chilled water storage type of system, so that we're not trying to account for a change in the evaporating temperature. I'm going to compare how much energy would it take for a given air-cooled chiller to meet a certain cooling load without storage, as opposed to having level load storage that will flatten the cooling load over the course of the day. So I got some characteristics for a piece of equipment, and we're assuming a sinusoidal outdoor air dry bulb temperature profile to use for condensing purposes, and again, same supply temperature, 4.4 C, for both cases. So here's the load profile that we're looking at. That's the inside one here. That's actually the school profile we were looking at before. And if I were to take all of the load represented by that curve and average it out, it would give us a plant that was sized according to this horizontal level load curve. And the other curve on this plot is the air temperature. So you can see that the highest loads on my load profile occur when the outdoor air temperature is the hottest, so we would expect that we would have the lowest COP for the cooling plant at that time. And if I can take all of this cooling load that we need to make above the plant capacity and move it over to nighttime when the condensing conditions are lower, then we're going to get some savings. So here are the chiller characteristics that I used for this example. It's less efficient than something you get today because this is a few years old, but the thing to point out here is how much the COP increases as the ambient air temperature decreases, and that's what we're going to take advantage of here in this example. So essentially what we did is run that cooling load profile through this chiller model using the temperature profile that was shown, and did that both with and without storage. And so the result is that with a load weighted outdoor dry bulb of 27 degrees when we're charging and 33 when we're discharging, that's a pretty big shift in temperature that will help us save energy. So the total chiller energy consumption with thermal storage is about 2,000 kilowatt hours, and without storage it's about 2,200. So there's a difference of 10% overall, which is fairly significant. And if we only look at the part of the load that was moved, what would it have cost to make that much capacity here as opposed to doing it off-peak hours? The difference is actually about 21% on average per kilowatt hour that is shifted. So a fairly substantial energy savings just from the day to night condensing conditions differing. This is some data from the system I won't talk about in detail in the case study. This is a district cooling system in which a large, what would it be, about 16 megaliter tank was installed for thermal storage, and the COP changed from 4.35 on average to 4.92 over an operating year between pre-storage and post-storage conditions. And there are certainly plenty of other examples of systems that have saved energy after a thermal storage retrofit. I don't expect anyone to read this, but it's documented in the link down here, and I imagine the slides can be made available to everyone. What it shows is a number of actual systems in California that were documented to have 3 to 50% reduction in cooling energy after a thermal storage retrofit. So that's the site energy angle, and certainly it's possible, believe it and have done it myself. Source energy and emissions, there have been several studies in the US that have looked at whether a significant amount of thermal storage in the general population of buildings would have a beneficial effect on the source energy use of the grid, and both of those have shown differing levels of improvement. So the California Energy Commission way back in 1995 was asking this question because they wanted to know whether they should give a credit in their energy standard for load shifting, which many standards did not. So time-dependent valuation, and they looked at 2 of their utilities and showed anywhere from 20 to 40% energy savings per kilowatt hour shifted, which is not inconsistent with what we just saw in that example. ASHRAE also commissioned a broader study in 2001 that looked at other regions of the US, and that study reported a 10% average energy and emission reduction for use of thermal storage. These savings come in one part from generating capacity, being able to emphasize the use of the most efficient generators instead of peaking equipment, which often is not as efficient and operates under conditions that are more taxing, and also from reduced transmission losses, so less I squared R type losses in the transmission system when the load is distributed. Another way that we can use thermal storage to help improve power production efficiency is through combustion turbine inlet cooling. Combustion turbines have come to be used quite a bit, especially for peaking power, and it's well known that both the peak output and the heat rate, the amount of power that has to go in per unit of output capacity, are inversely proportional to air temperature. So the hotter the air gets outside, the less efficient and the lower the output of the peaking turbine, and so it's a good energy trade-off to spend some energy to cool the inlet air, and that can be done in a number of ways. It's done with evaporative cooling, which of course is hard on water use and only gets you down to the wet bulb. It can be done refrigeratively, both with electric vapor compression or with absorption. Both of those, to differing extents, require energy at the same time that would be deducted from the net yield of a turbine. We're doing fine. And so the possibility of having a system that is low cost, probably electric vapor compression that uses thermal storage, so we use off-peak electricity, is going to give us the best output and actually quite economical. And one more example that everyone understands is combined heat and power. We know that if we use an energy source, say to make power and then take the heat and use it for a useful heating purpose, that improves the overall efficiency of the system. So we could go from less than 50% to over 75% efficiency by doing that. The important thing about combined heat and power is the first word, combined. You have to be able to have simultaneous loads to take advantage of this, and they often aren't simultaneous, and we find that using thermal storage is an important factor in maximizing the potential to utilize CHP. And then finally, this issue of renewable energy. We have intermittent electric sources from wind and solar. We see in places like California that we're getting new and strange shapes to our demand curves. Here's solar during the day coming up very large and then going away. So we actually find the highest demands as the load starts to taper in the evening because the solar is going away. And so we need to respond to that to make it feasible to use, technically feasible to use our renewables. Thermal storage is a good way of responding. And the other issue is storage with batteries that's been widely discussed. And we hear many folks saying that if we could just get to $100 or a little bit less than 100 euros per kilowatt hour, we would be able to make battery storage cost effective. And some of the data that you can find on this suggests that we're pretty far away from doing that. But if you consider thermal storage as being a way of taking electricity that you would have used at one time and putting it away in the form of cooling capacity to use later, we're actually able to do that for $1 a kilowatt hour or less. When I was on sabbatical in Denmark in 2016-17, I heard some presentations about thermal storage that they're using with their combined heat and power district systems up there, where they're doing it for under a euro a kWh. So it can be done, and I think it's a big part of the future. We should not spend all of our time trying to come up with new technologies when we have perfectly good ones that are just not being used enough or properly. So to conclude, thermal storage is a mature technology that was used for one purpose but has now been reimagined as something that we can use to support sustainability in a number of ways. And I've tried to indicate what some of those are. I think this points to the general principle that when we start thinking about what we'd like to accomplish with any type of system, we're better able to do that, and we can incorporate that into our practice without too much trouble. And so with that, I will show you a picture of a pretty tank, because some people think tanks are ugly, and thank you for your attention.